तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We were looking into the design of DCT queue, and we have covered a novel algorithm for implementation of same with a view to speed up the throughput, and we also considered the architecture earlier, and we are about to start the Verilog codes for the same design. And before we start this design, let us have a look at the image, how it is going to be processed, what the resolutions are, and what does color mean, and all the rest of it. So what you see here is a very high resolution picture of a bird here, and you can see that resolution is 1024 by 768, and it is true color, and you may not be in a position to read here, and I am just reading out for your sake, and it is written 24 here. This stands for true color. That means to say there are 3 color components in this, and depending upon the type of picture that you have, there are different formats, for example bitmapped pixel. So right now what you see is that particular thing, and with an extension of .bmp, and there are other files called raw. In raw files, what we have seen earlier as a gamma corrected RGB will be available in a raw file, and this is with there are other files like JPEG, which is a compressed file, whereas BMP and raw files are not compressed as such. And we also have one more type called TIFF file, which we will be requiring for MATLAB and other codes, which we will be describing later on, in order that we may use it for generating these pictures in a form that is that can be input to the simulator. And here you see it's a very high resolution here. Even if I increase the zoom, you still see a very good picture there. And so similarly, this can we have a special software called XNView, the site of which is given at towards the end of this lecture, and you can download from there. And using this, you can have resize, and there are they're all menu driven, and you can resize and do cropping, and so that we can extract from the picture of 1024 by 768 pixels, we can get 256 by 256, and that is what you will be seeing here. And you can see that the picture is not that good. You can see some information being lost. This is because it is 256 by 256, although it is continuing to be a true color here. And if you zoom both these pictures, for example the first high resolution picture, if you zoom, you will get all squares, and each of these squares is known as a pixel, and collection of 64 pixels, that is 8 by 8 pixels, we take in order to process a DCTQ, and that is referred to as a block. A block consists of 8 by 8 pixels, and each of the pixel, if you examine very closely, you will see that one particular square has only one common intensity all through, and this is because this is a pixel, and if you zoom further you can't go deeper into this, deeper than pixel you can't see anything, and naturally if it is a true color, this will be of order of 24 bits representation, and for each of the 3 color components you need 8 bits, and the software can also help you in converting this into a monochrome image if you desire one. And if I zoom, this is for 1024 high resolution into 768 resolution. Note that you can't make out anything here except perhaps the eye here of the parrot, and if you see in the second one, which is also a zoomed version, you can see the parrot here to some extent, and once again you can see the pixelations here, and there is a mark here for 8 by 8 pixel block, and you can see a much wider area covered. That is because it is for a lower resolution, and the resolution is 256 by 256, and once again it is true colors. And now we will continue with the Verilog design. So I will read out this to start with. This is the top level design module for the computation of DCTQ. The design file is dctq.v, and DCTQ prepares the ground for effective compression of data, especially that from images, whether it is still or motion pictures. The motion pictures are also referred to as video sequence, and 2D DCT is a simple 2-stage multiplication of 3 8 by 8 matrices C, X and CT, which you have already seen earlier, and input for this DCT is a block, which we have seen in the image just now, and it is 8 by 8 pixels as mentioned before, and DCT produces 64 coefficients. The first coefficient is known as a DC coefficient, while other 63 are known as AC coefficients. This also we have seen earlier, and mind you, what we are doing is we are looking into the actual DCTQ design file, that is a .v extension, and DCTQ.v is the actual design file. Then what is the need for putting all this as comments in this is, it is a ready reckoner for a designer or anyone else who is verifying the design, and so that he need not go and look into the massive document that we have covered earlier, and that is why it is saying here, please see the DCT document for details if should you require more details, and the resulting DCT is divided by the corresponding quantization value stored in 64 byte ROM/Q.v, and address serves as the address for the DCTQ coefficient. Address equal to 0 would correspond to DC coefficient, whereas all others are AC coefficients up to 63, and this design earlier, if you remember, we have seen bottom up approach of the design, and herein what we will see the reverse, that is top down approach of the design, and in the sense that in earlier bottom up approach we started with the lowest modules such as RAM-RC, and then we went on to a higher level which invoked this RAM-RC, and that higher level is dual RAM. Like that we went on from bottom to top, and now what we see is the top is the very design file, and DCTQ.v is the top design file which we are seeing right now, and this one it will merely invoke different modules or submodules down the hierarchy, and here what is included are precisely those modules. For example, RAM, RC, dual RAM, which we have covered already, the design of which we have already covered, and so also we have covered ADAT 12S, and 14SR was given as an assignment to you, and what we are yet to see is this DCT reg here, and in order to store the partial products of CX matrix computation, if you recollect our architecture shown before, and we have also used seen the design of multiplier for 8 U into 8S. U stands for unsigned, S for signed, and as usual we also gave assignment for 2 other multipliers, and that is precisely what we are going to use here, and we also covered the design of ROM-C as well as CT. So this is the C and CT matrices for the evaluation of DCT, which requires the multiplication of 3 matrices C, X and CT, and we also had a quantization table. It is actually a reverse or the inverse of the quantization table, and this also we have seen earlier, and we are yet to see the next one. This is the last module, which is called the controller, and any design is dependent upon how good a controller design is, and it is always a good practice to have a separate module for the controller, as we see here. So, this is the top level module for DCT-Q. Before we go into the details, let us point out one fact. So, we know that FPGA and ASIC based designs are massively parallel and highly pipelined, resulting in very fast implementations. This is in contrast to the conventional approach of using a Pentium and or DSP using either C language or assembly language, and all of which are mainly sequential in nature. So, if you have a computation of the order of n cube or even more, n is 8 in this case of DCT-Q evaluation, and huge number of computations are involved. Naturally, these sequential machines, basically like Pentium, DSPs, will take quite a lot of time in order to process even single frame, and in order to get a real time image, it may be you may have to scale down the picture resolution maybe to 352 by 288, which you see right as a CD as in MPEG 1 format, and probably this course is going to be on such CDs, and you will be seeing 352 by 288, that is what is called QCIF, and 288 I am not sure, you can cross check in any textbook, and that means to say we can only process very low resolution picture using Pentium, etc. If you really want sophisticated system, you need to go for either FPGA or ASIC based designs, and so this is the top module we declare here. DCT-Q is the design, and these are all the signals that you have seen before in the form of a block diagram shown earlier, and I do not have to go into all the details. The final output is going to be DCT-Q, and when it is valid is indicated by this signal, and its address is also given by this signal. So, what you have put there we declare as either input or outputs, and that is precisely what you see here in the next few instructions, and along with the size of this signals you see there. For example, address is 6 bits here, and DCT-Q is 9 bits, and DCT will be 12 bits, and so on. And if you remember the first CX multiplication, we used 8 multipliers. They are all they produce the outputs result 1, and they are 16 bits in width, and they are listed here result 1 through result 8, and finally we added all this in order to create one partial sum, and that is declared here, and this is by means of an adder and 12s if I recollect, and there is also another DCT which we need, which is of 12 bits size, and sum is only 15 bits here, although high precision is being truncated here. We will look into that details later on. Then we also used a dual RAM, and there are 2 outputs, namely D1 and D2, and they have got to be declared, and as wire. Why it is wire, we will come to that little later on, and we also have to have partial products stored, and this partial products P naught etc. we had used earlier. You may regard it as Q or not Q or 1 and so on, and row wise it will be different, and size is 11 bits. And at the second stage we take this partial product and multiply with CT to produce independent multiplied results. They are all indicated as RES1 through RES8, and now notice that the bit precision has improved, increased quite a bit, and then we will be needing some counters in order to realize address generation as well as address for the ROMs, RAMs, etc., which we use in our architecture, and these are all generated in the controller. and this is for quantization table. We have a ROM and whose output is Q out here, and an important thing here is a good design practice is you should not have any logic on the main design, that is the top design. So, what you should have is only just calling all sub modules here. For example, dual RAM is being called here, and that is what is indicated here. Dual RAM to read image input block 8 by 8 pixels, this is read block by block, and this is the X matrix that we have, and one row of a particular block is being read at one time. Every clock for that matter, we read keep reading every row in a block, and so in order to do read that one into the RAM, we have to invoke a dual RAM here, and this is the instantiation, and these are all the signals that you are already familiar, and only difference here is we had in dual RAM we have basically two modes. We can either be in read only mode or write only mode. To start with, it will be in write only mode, and this R and W signal is what is being used for that, and while in write mode, read mode, we execute the DCT queue, and this read address will be delivered from the controller, and by using a counter, and the same counter is also used for ROM later on, and ROM for C and CT matrices. And note that only 3 bits LSB is used for X matrix, because in the first computation of Cx, we take a row of C and then take a column of X matrix, and repeat the same for other columns of the X matrix. That means to say we advance to the next row of C only after processing 8 columns of X, and that is the reason why this is put as LSB, and the MSB for the counter, that is 3, 4 and 5 will be for the C matrix, which we will be seeing later on, and the final output of the is D naught here, and this is applied to the second stage, which we will be covering shortly. And dual RAM has 2 pipeline registers, which you remember as one after RAM, which is being called by dual RAM, and also another at the top level of dual RAM. So, 2 pipeline registers are inside the dual RAM. And next is we have to use ROM, which stores C matrix and CT. C and CT, if you notice, they are all nothing but the same matrices. One is to be interpreted as a regular matrix, whereas the other one is a transpose of the same matrix. So, here in this case both contents are same, that is the reason why we just use single ROM. This design also we have covered earlier, and so here what we do is we do not take just C value alone, we take just twice the C value and later on divide by 2, so that functionality is not changed, but yet we increase the precision and while processing, and that is the reason why this trick is adopted here. And both these require row accesses for computation of DCT, and next step is to call the ROM C and CT module, and you remember that we have 2 addresses, address 1 for C matrix retrieval and address 2 for CT matrix, and as I mentioned before, MSB is used here for C matrix here, and note that 5 to 3 is the MSB of the counter 1, whereas LSB is for X matrix, which we have seen just now. And in addition to this, we also need CT matrix, and that is available by accessing through this address, which is given from counter 3, and only 3 bits will be there for this counter, and this is for CT matrix, and out comes 2 corresponding data, and D1 and D2, which we will be using subsequently. Here ROM, that is ROM C.V, which is the one of the submodules for realizing CCT ROM, also has 2 pipeline registers to keep pace with dual RAM. So, we have to evaluate Cx. So, unless ROM which has C content and dual RAM which has the X content keep pace with each other, you will not get any meaningful result, and therefore pipeline register has been increased to 2, although only 1 is required here, and just to keep in step with the dual RAM. Address 1 and address 2 are for fetching C and CT matrices. C is used in the first stage multiplication, and next what we are going to do is having got C from the ROM, and also x from the dual RAM, what we need to do is do the multiplication. Remember that we had 8 multipliers in the architecture, and we will be invoking 8 such multipliers, and for that you each of them instantiated as U11 through U18, and similarly we need to evaluate outcomes result which will have to be added, and the added result will again be multiplied by another set of 8 registers in order to have the last DCT produced using the CT matrix. CX is computed using the following 8 multipliers. D0 is the image input, X and D1 the C input, which we have seen before. D0 is unsigned, while D1 is in 2's complement, and the entire thing is generally in 2's complement, all the computations everywhere, and result is in 2's complement. So this is the first of the set of multipliers which numbers from U11 through U18, that is 8 multipliers, and at each step this one will be the X matrix, and notice that only 1 byte is covered by one multiplier, and corresponding C value is available here. Once again the corresponding byte is taken in order to process, and it produces a result called result 1, and this is 16 bit because it is 8 unsigned into 8 signed. So totally it will be 16 bits, and likewise for all the 8 multipliers are identical except for the fact that different bytes are used. Next 8 bytes are used here in this case, and producing result 2, and so on it goes. See here U13, U14, and notice that the bytes are different, progressively less, U16, U17. Then this is the last multiplier in that set. So it is processing the very last X of the if you take a row, the very last pixel which is being taken. It could be either last or the first, it is immaterial, because so long as you take C and X the identical bytes, only thing you have to keep track of what you are doing. And so this at this step we have multiplied and got 8 results, result 1 through result 8, and next step is to add these results, 8 results that we have got, and by using added 12s which we have already designed before, and these are all N0 through N7 or nothing, none other than this result 1 through result 8 which we have got before. Note that we are dropping some bits here because that much precision is not really required. So at this step, if you take the model sim results and ponder over the waveform, you will notice that it will be of the order of some in decimal number, some 156. This is only a typical example has been given for one of the results, and other results will be hovering around this. And after this, the point here is, I want to point out that there is a decimal point here, and after this 4 bits. So it is a mix of decimal number and binary number. Just to point out the decimal point, after the decimal point there will be 4 digits here, and this adder, as we have seen before in the design, it has only 5 pipeline stages, and output is not registered. This is not registered because we are going to register with the next module that we are going to look, that is called the DCT-reg, and up to N7 you have here, and note that we have dropped 4 bits here because we do not need that higher precision, and these precisions have been basically arrived at after a few iterations, and looking all keeping in mind the quality of the image that we create, and we have very high precision computation of same DCT-Q and reconstruction in MATLAB, and that serves as the standard reference for the computation of the quality. And when after truncating this many bits, we always compute the PSNR, or what is called a image quality, and compare it with the same corresponding MATLAB output, and if it is quite close, say of the order of say 0.5 dB, and maybe that is a 2% accuracy we can say roughly or less, and then we truncate as per that. So that is how we do the truncation here, and here there is a 3-stage addition. This is the summation that we are doing, and as a result we started with 12 bits as the input for each of these numbers, and it final result after addition will be 3 bits more, because at every stage of addition you have one extra bit if you add two numbers, and that is how we have 15 bits here, 14 through 0 as the sum here, and this will have to be stored in the as a partial product. This is the actual partial product P which we had seen in the algorithm before, and that is what this module is going to be doing, and it has one input that is basically the same thing here, and once again we see we drop some more bits here, and because otherwise it will become too unwieldy with the next stage, and anyway it is producing the desired quality, and there is also a reason why we drop one more bit here. We will just have a look at the comments here. This is actually 11 bits signed integer, and there is no decimal point here, and we drop 3 bits after the decimal point, and in addition to this we also drop one more bit, because 3 through 0 are dropped, that is 4 bits are dropped. So 3 bits have been accounted here, and another bit we are dropping which is equivalent to dividing the result by 2. Any right shift, as you know, is equivalent to dividing by 2, and that is because we had taken earlier, in order to increase the precision, 2C not C, but we actually need C here in order to have the right correct result, and for that we drop one more bit, which is equivalent of dividing the result which contains 2C and into getting a result which contains only C. ROM, and hence one more bit is dropped, that is what we have here, and same is true for CT as well. And here we have 8 registers which will register all the partial products generated in the first stage of multiplication, and you need to write it into the appropriate registers. For that you need an address, 3-bit address, and because there are 8 registers you need 3 registers and 3 bits here in order to write into that, and this set of registers are called QR0 through QR7, and this writing will be enabled only if enable counter is enabled, actually it is 1, and each of these partial products will be 11 bits signed as explained before. In the second stage we have another 8 multipliers, the set has 8 multipliers here, and in this case we take these partial products which are QR0 through QR7, and you can see here as one of the numbers, and the second number is the actual CT, and this partial product which is nothing other than Cx, and we need to multiply this with CT matrix in order to get the final DCT. That is what we are doing here. We need 8 multipliers, and all these multipliers will be working simultaneously, concurrently, and that is the beauty of FPGA ASIC design. Now you would have noticed that we have so many hardware so far. So far 8 multipliers and 1 adder we have seen. In addition to that, all the other hardware such as other 8 set of 8 plus one more multiplier and adder and so on, all of which actually work simultaneously, concurrently, and that is the beauty of this FPGA ASIC design, because we to start with said it is massively parallel, and that is how you have a massively parallel design, and this particular design has totally 17 multipliers in order to have a DCTQ as well, and we also had ROM, etc. All of this work concurrently for fresh data being input at every clock cycle, and this is the CT input here, and once again we apply only 1 byte at a time, and this is 11 bits, this 8 bits here, and result naturally will be 19 bit, and we call it RES1 to RES8, subsequent 8 multipliers, 2 more multipliers here, and each time you can notice that we are once again taking different byte order, and finally the last multiplier in the second stage. Thus we have seen 16 multipliers being used, all of which work concurrently, and RES1 through RES8 is the final result, and when you add this in the next stage, which is adder with registered output, here this was given as an assignment to you, I hope you have done, in which case you can readily use the design, and you notice once again we are dropping some more bits here, and for the same reason, in order to I mean so that the quality that we get is already satisfied even if you drop so many bits. So, here you are dropping nearly 5 bits, and as an example for this value decimal point is here once again, and we add all the result 1 through result 8 here, and finally to get a DCT. And when you add this one, you would notice that it is 18 through 0, we have dropped some bits here, and in spite of all that the number of bits, this is 14 bits, and actually it will shoot up to 3 more bits because adder has 3 stage of addition inside pipeline, and therefore it will create 17 bits totally. This is 13, 14, and that will be 3 more bits. So, 17 bits will be there, out of which we need to extract only few number of bits, and this is only 12 bits that is required, and once again we are truncating here, and this truncation is done right within the adder itself, and you must also do the same thing when you do this design all by yourselves. And this is the final DCT output, and we have to get the DCT queue output from this, and this is in 2's complement. And one more point is this DCT 12 bit has not been put arbitrarily, but this is the requirement for the standards JPEG through MPEG standards, and that is the reason why we adopt 12 bits here. This adder 14 SR.V has 6 pipeline stages because one more stage is required when compared to 12s, and that is because of the registering the output. And next stage is to invoke the quantization matrix, which contains actually 16 divided by the quantization value. So, inverse quantization value is being taken here, and in order to increase the precision as we had done before for C by multiplying it by 2 and then later on divide by 2, here also we adopt the same trick by multiplying it by 16, and later on we will divide by 16, so that the value is not changed as per the algorithm. And here this in order to retrieve this quantization this value here 16 by quantization value. So, what we need is an address for the ROM, so that you get at the output Q out the actual 16 by quantization value, and counter 4 generated by the controller does supply this address here. So, here after invoking that ROM, we need to multiply in order to get the DCT queue from DCT. So, one input for the multiplier will be the DCT, which we have already seen, and Q out is nothing other than the 16 by quantization value, which we have just now seen in ROM queue, and that is being fed here, and you will appreciate the feature of calling ports by name here, because now right now you can see all this. And earlier right at the beginning I mentioned that we have declared this as a wire here. Now, from this it should be apparent what we are doing here is from one module we are connecting it to another module, and inside that module it will have the very same name here, and because we are making a physical connection like a wire or a net, it is called wire, and you have a Q out here, which is a ROM quantization table, that is this one, and finally out comes the DCT queue here, and this also has 8 pipeline stages, and so overall pipeline stages if you remember in the architecture we have seen it to be 45, and when we see the actual waveforms we will understand this very clearly. And 16 by quantization value is multiplied with the DCT output above to get the final DCT queue output. Result is divided by 16 in mult 12s into 8u module to get 9 bit DCT queue. Once again this 9 bit is dictated from the JPEG MPEG standards. In order to conform to the standards, it has been taken as this 9 bit, and N1 is DCT signed 12 bit, this also as per the JPEG, and N2 is unsigned 8 bit decimal point before MSB. This N2 is the 16 by quantization value, and after the decimal point starts the actual value, and that is what is mentioned here. And this DCT Q 8 through 0, that is 9 bit, conforms to JPEG, MPEG 1, MPEG 2 standards, and etc. probably stands for H261, 263, and there may be other standards as well, maybe HDTV. So, DCTQ valid is asserted whenever DCTQ is valid and address provides the address of the DCTQ quotient. We have seen this before. Address equal to 0 is the DC quotient, 1 through 63 are all AC quotients. Higher the order, higher the frequency. And finally, what before ending this design, we have to invoke a controller, which we have seen the need for same, and it has various signals here, and when we take the details of controller, we will describe all this, and it is only once again we call by port names, and these are all start pins, etc. we have already seen R and W, and these are all the outputs generated by the controller, and different counters, and the enable counter 2 as well as enable partial product register, and different registers are all there. This is counter 5, or we can rather take it as address file, address register, in providing the DCTQ quotient address. And this is the end of the module, top design module, and now you would have noticed an interesting feature which I have explained right in the beginning. There is no logic in the top design module. It is merely calling the different modules that you have seen here, everywhere just calling the modules adder or multiplier as the case may be. And a good design practice, once again to reinforce the statement, is to avoid any logic on this. So, next we will consider some of the files, submodules which we have not seen before. One is for the partial product, this is called DCT reg 2 into 8, means some 16 registers are really required, and the width also we can program here, and that is why n is put here. If you do not like this name, you can change it to partial product PP or some like that. A set of 8 11-bit registers, that is QR0 to through QR7 to store the partial products P of CX is created in this module. So, this is the module declaration here, and it lists all QR0 through QR7 outputs here, and these are all the inputs, and data in is what you have after the first adder, the 12S adder that we have seen, and that is the partial product that we need to store in, and at every clock a new data will be coming in DIN, which we will have to route it to one of these registers. For example, with the arrival of the first clock, you will route it to QR0, and then divert the next data at the next clock to QR1 and so on, and at the 8th clock you will input into the QR7. And as I mentioned that n is a programmable thing, so you can do this by having a special C like instruction here. We can declare any variable here and assign some known value. For example, width has been assigned 11 decimal here, and this is by declaring it as a parameter, and once you declare this, you can instead of writing 11 at every point of time, we need to only write width here, and that is what we have seen here. This is the output width, that is for register size here, and if you take 11 here, 11 minus 1 is 10 here, so 10 through 0, that is 11 bits for the QR registers. Similarly, data in also must have the same width, that is why this is put here, and then the 0, 1, 2, 3 are basically addresses for the register to point to the respective register, and that is done by this signal, and which must necessarily be 3 bits in order to have total 0 through 7. And once again we have declaration of reg and the width once again given, and all these registers we use in always at positive edge clock, and this is the clock that we are referring right now. And in this block, what we are going to do is simply assign data in value to different registers depending upon the write address, and the write address is also one of the inputs. If the address is 000, then we take whatever is the input at data in and merely copy into Q0 register. Like that, Q0 through Q6 will be used for different addresses, and before this we can do all this only so long as this chip is enabled, that is enable reg is one of the inputs, and this in turn is from the enable counter 2, and only if it is enabled this will take place, and with the arrival of the first clock this write address will be 0, and with the next clock it will be 1. So, every time it will go through one of this here case and hence the case statement is used here, and like that you have Q0 through Q6 at arriving at different clock cycles one after another. Finally, you will have Qsun also assigned, but not here, but here towards the end. Why, I will explain here. This is being assigned here, and instead of putting this for this statement with this alone, so we have done some more thing which will take some more registers for this. The reason is as follows. See, first once the arrival of this 7th clock cycle, this has been written, and with the 8th clock cycle the last partial product is written. So, these partial products which we have written, if it continues to be in same Q0 register, with the arrival of the next clock, that is 9th clock, this Q0 will be overwritten. So, the partial product will get lost. So, in order to avoid this, and remember that we need the partial product for the computation of the next stage, and for which you need further 8 clock cycles. So, that means to say this partial product will have to be stable for next 8 clock cycles. That is possible if you write at this stage, and here into Q another register called QR0. So, with the right at the 8th clock cycle, we transfer all this Q0 through Q6 content into a safe register here, and as well transfer the last thing which we have not done before here into this. Now, with the arrival of the next clock, this Q0 will be overwritten, but not QR0. The QR0 will be overwritten only with the next cycle when after all the 8 clock cycles. So, thus if you examine this one, this will be available for the next stage computation to the tune of 8 clock cycles, and this completes that DCT register. And next is the DCT-Q controller, and so these signals are listed here, and we actually have different inputs, reset, start, hold, ready, and these are all the outputs. R and W is to switch from one RAM to another inside a dual RAM, and when DCT-Q valid is to be given, all that is covered here, all the counters. So, also the address for the DCT-Q coefficient, and address is same as counter 5, and we list here all the declare all the inputs as well as the outputs, and so also the counters and their bits here, and declare reg once again, and regarding the outputs here, and as I mentioned before, we have 4 counters, 5 counters basically, and they also need enabling of those counters. So, we declare them as reg here, and we also need intermediate results for which we will cover later on, and for that these are all the signals that we use, and we also need pre-incremented signals, which is basically using assign statements, and they are declared as wire here, and the actual counter one reg is this one, which is pre-incremented here, and that is what is done here. That is what is done here, including the DCT-Q coefficient address. And now, very first counter we should enable only if this condition is met, and it must be disabled when this condition is met here. The first condition is when we give the start signaling that DCT-Q process must begin, then what happens, that is after a delay this start reg 1, which we will cover at the last of this always blocks in the controller, and if it is 1, this equivalent to start being 1, and with a clock cycle delay, and if it is 1, so long as it is 1 and the counter reg is 0, which signals that it is yet to start right at the beginning we are. When these conditions are met, then only we will enable the first counter, and the same counter is disabled if last of the block is processed. For example, start is continuing has become 0, and in which case when the counter value is 63, only then we disable the counter. So, otherwise not. Note that it is for 0 as well as for 63, not any other combination. So, here we have a set of always block here, and they are all identical. First we initialize each of this enable counter 1 through counter 5, and if it is hold we just do not disturb the contents, and we enable this only when a particular condition is met. This condition we have already seen before, and only then we enable the counter. Otherwise, if a disable condition that also we have seen before is met, then we will disable this. Putting a 0 into this is equivalent to disabling. So, exactly the same thing you will see, and otherwise do not disturb here for all the other counter enables here. So, once again you see in the design one signal in only one always block. This is a good practice, I hope you will follow the same, and if you take hundreds of signals in one always block you will get drowned. So, it is a good practice to have just one signal, and very rarely violating that if the need arises, which we may see later on. And similarly for reset, hold, etc. same, and it has to be cleared if counter 1 is to be disabled. And here we remember that we need a partial product to start with. So, that will be active, that DCT reg we have used, that should be active, that should be enabled only when the actual counter 1, which starts right from beginning when the start is given. When it is 14, only then it will be right time for enabling the counter 2 as well as the DCT reg. That is what we are doing here, and that is for 14 decimal. Likewise, we will be doing the for different pipelines we have covered earlier. This is for the DCT reg here, and this will be understanding very clearly when we look at the waveform. This is for enable counter 3, and exactly same, everything is same except for 20 this is being done, and this is for CT and ROM CT access here, and counter 3 is enabled when counter 1 reg is 20 decimal. Of course, it ROM CT has 2 pipeline stages, and therefore the 20 is arising. And similarly for counter 4 exactly the same, except once again it is a different value here for 35, and for counter 5 this is at the quantization ROM here. So, when the quantization ROM must be enabled is governed by this 35 of counter 1, and similarly when DCTQ must be valid is determined at 44, and exactly the same thing which we have seen before. And you have seen in the architecture that we had totally 45 clock cycles delay, and this starting counter starting from 0, 1, 2, 3, 44 is exactly 45, and this explains why 45 pipeline stages were there. And this one is for the actual counter. The counter is also exactly similar to enable, except that when the counter is enabled it will be incremented. So, counter 1 next was actually counter 1 reg plus 1 pre-incremented, which we have seen before, that we assign only when the counter 1 is enabled, and similarly for all other counters here. You can see once again reset, hold, and we increment only if enable counter 2 is high, and same is the case for counter 3, and increment only then, and so also for counter 4 as well as for counter 5. So, here that is for counter 5, and so here what we need is we need to differentiate between very first block and of processing and subsequent blocks of processing. That is possible only by having one signal here, and it is just a single bit. If initially it is initialized to 1 and when with power on here, and this is meant for changing the R and W signal, which will suppose you have written the very first block, after that we had to change this R and W signal, and this is so only after writing the very first block having written. So, we change that at that point of time, and also switch over to different R and W value, so that we can take in next block of data and start processing the first block of data. That is what we are doing here, and this is depends upon the start being 1 here, and similarly this is for the ending of the block. When one block is completed, this counter edge completed in sense the data has been consumed, DCTQ is not at output, only the data has been consumed as far as one block is concerned. So, that signifies if you read the counter 1 as 63, it means it has just consumed, and start must be continuing to be 1. Under this condition, what will happen here? So, this is the condition. So, what we had to do is we had to invert not only R and W, but also force this counter 0 to 0, because for subsequent blocks this is forced to 0, and therefore, this will not come into this category. In the future it will not come to this category, and this was for the end of the block we have seen before. If it is end of the block, we take merely invert it, whereas in the previous case it was to take differentiate between the very first block and subsequent blocks corresponding to counter 1 being 0. That is why that trick was played there, and this is done as a routine affair here. Similarly, we create a ready signal, and for this the condition is start must be still 1 and counter 1 is 1, because after this we want to take an action. So, we will continue this in our next lecture. Thank you.